The DFT, Discrete Fourier Transform, is a workhorse in signal processing. It is different from the discrete time Fourier transform in that it is discrete in both time and in frequency. And not only that, it is finite in both time, extent, and in frequency, with some caveats there. And we'll talk about those as we come along. We'll start with the definition of the DFT. As you can see, this has a form very similar to the DTFT. One of the differences is k instead of omega. I've used the square brackets to show that k is now a discrete value. In fact, it ranges from 0 to n minus 1. And instead of e to the negative j 2 pi omega n, we have e to the negative j 2 pi k over n, capital N times n. So a difference there. Note that this is often written this way. I prefer the way I've written it first, but you should be familiar with both ways because it appears both ways. And in fact, sometimes we'll, even though it's not my favorite, we'll go ahead and we'll use this W format, because when we're, for example, developing the fast Fourier transform, it really helps to have something a little more compact. DFT. So the inverse DFT is actually a definition that's very similar to the forward DFT, which should be pretty nice because we're tired maybe of having path integrals or integrals from minus infinity to infinity or 0 to 2 pi or whatever it may be for transform du jour. It's just another sum. In fact, the only way it differs from the forward DFT is that we have the 1 over n out front, and the sign on the j component has changed. You'll notice that the sign on the w is opposite of what it is on the e, because w is defined as already having the negative exponent. So IDFT is short for inverse DFT. Just be grateful we're not saying inverse discrete time, discrete frequency Fourier transform. It's much easier to just say DFT. Now this is defined, if it wasn't apparent yet, over just a limited range of n. And remember, we had all sorts of problems trying to compute the DTFT in that it was infinite in time and continuous in frequency. Now we have something that is finite in time, finite in frequency, and discrete in both. We're actually going to talk more about the relationship between those as we move along. But the first thing I want to do is relate this back to what we've done so far. So the DTFT, as you might recall, is defined in a similar way, except that we go from minus infinity to infinity. Xn e to the negative j omega n. And the DFT is just a sampled version of the DTFT. This has some implications we'll talk about. It's sampled not in time, it's sampled in frequency. When we sample in time, we know that we have to take care, or we could have aliasing in frequency. When we sample in frequency, we also have to take care, or we can have aliasing in time, which is kind of weird. So we'll put that in there in just a moment. Another point I'd like to bring out, actually, while I'm at it, we should probably just put here in the notes that the DTFT is hard to compute because it's infinite. And the next point is that the DFT is a basis expansion. So I don't know if you feel the same way I did, but I wasn't, when I first took linear algebra, I wasn't convinced that it was going to play a big role in my life. And I especially couldn't quite figure out what was going on with eigenvalues and eigenvectors. Sure, I understood it. I took the exams and so on and so forth. But they're coming back in force. So if we define an inner product, x with y, and these two are vectors, so maybe I'll try to make them bold. Then if we define that as y Hermitian x, where y Hermitian is equal to y conjugate transpose, then we can think of the DFT as a basis function for this particular inner product. So let's review a few things here to bring this together. First, for orthogonal vectors, let's assume we have some basis set. And the set would be V indexed by I. Recall that we would have V I comma V j is going to be 1 for I equals j and 0 otherwise. So we're going to define a set of vectors V as follows. I think I'm going to have to go on to the next page to make this fit. Okay. So we will let, in this case, Vk, and we'll define it as 1 Ej 2 pi k over n. So next one would be e to the j 4 pi k over n. And these entries take up a lot of room. So all the way down to e to the j 2 pi n minus 1 k all over n. So for a particular value of k, which we're given because this is v of k, each one of these is going to evaluate to a complex number. So let's see how we're doing here. If we take Vi, inner product, with Vj, we're going to have these two vectors, and I hate to write this all out again, but I'll do a little bit. 2 pi k over n, like so. I just realized that using a j up there with the imaginary j is perhaps a poor selection of notation. So I make my j's different. I hope that's enough to differentiate them. But for now, this is going to equal 1 plus e the j 2 pi over n times j minus I plus e j 2 pi over n times, I'm sorry, that's 4 pi over n, 4 pi over n j minus I, and so forth. So, for starters, if j is equal to I, then this is equal to 1 plus 1 plus 1, and so on and so forth, which is just n. Well, for orthogonality, that's okay, but for orthonormality, this is not. So, if we want this to be orthonormal, we have to put 1 over the square root of n out front. Now, we haven't yet established that it's even orthogonal, and we're already talking about the normalization. We'll get there in just a moment. I should add that if you're in other disciplines, physics or math, they usually do define it with a 1 over the square root of n out front. If we did that, that would change the DFT to have a 1 over the square root of n in front of the forward DFT and a 1 over square root of n in front of the inverse DFT. Well, that seems a lot more mathematically elegant. Why didn't we do that? I think it was for historical reasons. With very, very weak computing power, when people wanted to do frequency analysis, multiplying by a square root was calculating the square root and then multiplying each term by that square root was computational cycles they didn't want to spend. And since all it did was change the amplitude, and they knew how much it changed the amplitude by, it was a lot more efficient to just leave the 1 over the square root of 2n out on the forward DFT. And then if you had to do an inverse DFT, you divide by n. And we're going to find later that usually we use n that is a power of 2. And so dividing by a power of 2 becomes, well, almost trivial. It's just a shift. So in signal processing, the decision was made long ago, for good or ill, to define the DFT without that up there. Okay, so let's go back and complete this and try to figure out if we actually have an orthogonal basis. So, in order to do this, we need to remember the equation for a geometric sum. Remember, if we have something of the form, the sum of alpha to the I over I, and in this case we know what we're going to start at 0, go to n minus 1, is going to be 1 minus alpha to the n over 1 minus alpha. So in this case, our alpha is equal to e j 2 pi over n, our other j minus I. So now we know what happens if j is equal to I. If j is not equal to I, j not equal to I. Then we have vi with vj is equal to 1 minus ej 2 pi over n j minus I to the n over 1 minus ej 2 pi j minus I over n. Well, that n and that n will cancel, and so we have e to the j 2 pi times j minus I, which is an integer. So e to the j 2 pi times an integer is just 1. So the whole thing here becomes 1. Now, we had to treat j not equal to I separately, because if it's equal to I, then of course the bottom is going to be 0, and we get it 0 over 0, and we have to do some sort of L'Hopital's rule or something like that. But here, we can just say this is equal to 0. So now we've established, finally, that we have an orthogonal set not orthonormal, but if I is equal to j, we get that. If not, we get 0. So, in this case, we call this the DFT basis, and we can actually project a signal onto the DFT basis by using the DFT matrix, which is made up of all of the basis functions and has lots of nice properties, some of which we'll get to as we go along. So far we've established, or at least I've given the definition for the DFT, stated that it is a sampled DTFT, and we're going to come back and revisit that soon. And then establish the fact that your linear algebra now actually is going to do some good solid work for you, in that the DFT is squarely in the domain of linear algebra, orthogonal basis analysis, and so on and so forth.